webinar, Innovation in Soil Flux Measurements. My name is Nabil Saad, and I'm the Senior Product and Application Manager for Soil and Agriculture. Today I have the pleasure to introduce my colleague, Derek Fleck, who is a presenter, and within this webinar, Derek is an application specialist at Picarro, and he was involved in the team for the development of the NIR G2508 system that is capable of analyzing concentration species. And this is part of his presentation that will show the comparison between the Picarro G2508 and the gold standard of gas concentration measurement for soil application, which is the gas chromatograph. I also have the pleasure to introduce Nick Nickerson from Forerunner Research. Nick is a co-inventor of the forced diffusion membrane-based technology and the chief scientist at Forerunner Research, Inc. Forerunner is located in Canada. It's a Canadian tech company specializing in gas detection hardware for academic and industrial applications. The agenda for today would be that we start with Derek Fleck with his presentation about continuous monitoring of greenhouse gases from soil respiration and the comparison with GC. And then we'll be followed by Nick Nickerson's presentation about trace gases, soil flux measurement, trace gases, and isotopic applications. Right after the presentation of Nick, we'll open the floor for Q&A. And then you can, in the meantime, keep sending your, typing in your questions, and then we'll compile them, and then during the Q&A session, we start addressing them one by one. I would like also to address a little bit the two types of analyzers that are involved in those two presentations. The first system is the Picarro G2508. It's either a closed system or an open system loop. And then also the isotopic carbon analyzer. In this case, I'm showing the G2201 system that's capable of analyzing isotopic carbon in CO2 and methane, but also there are other variations within Nick Nickerson's talk about a different isotopic carbon from Picarro. Speaking of isotopic carbon, I would like just to talk a little bit about isotopic soil flux, and then show how the fractionation of carbon can be used as a tracer within soil and the carbon system, including the soil respiration. So you have, as you see, these values are approximate. You have the atmospheric CO2 that exhibits a delta 13C of -8 per mil. And then you have the photosynthetic uptake from -26 per mil down the stem, then the root, then you have the soil respiration that goes up. Part of this gets recycled through respiration, and then we have the net CO2 exchange going up to delta 13C -27 per mil. And again, these are all approximate values. Nick is going to show how isotopic fractionation of carbon is very informative in the case of calculation of soil flux. Right now, I'm going to cede the floor to Derek Fleck and his presentation on continuous monitoring of greenhouse gases from soil respiration using closed soil chambers. Derek, it's yours.
Thank you, Nabil. So I'll be talking today about a comparison of the G2508, as Nabil said, with the gas chromatograph. And it's basically just to answer the question, the number one question that we got when we developed this analyzer, and it's basically, how does it compare to a GC? And that, of course, is the goal of this. It's to grab side-by-side measurements with the GC and the G2508 of the same exact soil flux events, and then calculate the error of these fitted fluxes to both the GC and the G2508. And what this will boil down to, as we'll see, is that we'll see the importance of this time resolution that the G2508 gives us. So just an outline, we'll talk about the instrumentation that I use, and then the cross-calibration of the instruments, accounting for drift in both instruments, and then the precision of a single measurement. And then we'll go through the experiment on what what I did and what the data actually looks like when you come out, and then eventually a comparison of the flux measurements. And then we'll go over everything that I talked about again in the conclusion. So first, the instrumentation that I used is, as we said, the Picarro G2508, which is a cavity ring-down spectrometer, which uses near-infrared laser diodes to look at absorption features to determine the concentration of gas in a sample. It's a continuous gas flow into the cell of the analyzer, and you get simultaneous measurements of nitrous oxide, carbon dioxide, methane, water, and nitrogen, or in ammonia. And we get a measurement interval for nitrous oxide of about 3 seconds and seconds for the other species. The GC that we used was the Shimadzu GC14A, and it's equipped with 3 different detectors, an ECD for nitrous oxide, FID for methane, and a TCD for CO2. And it takes a 5 milliliter sample injection on a 1 milliliter loop. So now that we know a little bit about it, we can look at just a rough estimate of our spec sheet. And these are the numbers that we promise that the instrument will do on a 5-minute average basis. So it's about 5 ppb for N2O, 5 ppb for methane. CO2 is 200 ppb, ammonia is 1 ppb, and water is 100 ppm. So these are all approximate. It's just specs that we have to meet, and analyzers will vary, but they have to beat this thing. So later on in the talk, we'll see that the precision is actually better than what we promised. So now that we know what the instruments are going to look like and what they measure, we want to be able to put them on the same exact axis, which is actually the most important part, since calibration of both instruments is independent and can vary from lab to lab and the practices that each person does. So what we did was we took 3 standards of each individual gas and then measured them 3 times in the GC with injection, and then we put that sample into a Tedlar bag and let the analyzer measure that, the G2508 measure that sample for 5 minutes, and then we can take an average to get a better precision on that one measurement. And then we do that with all 9 samples and then fit a linear relationship to what we measure on the G2508 to what you measure on the GC. We actually can see that we get really strong measurements for the linearity between the 2 analyzers, which is very important. And the R-squared values are, close to 1. Now we can look at the precision. Now that we have the absolute accuracy down, we can look at the precision of each measurement. So how we do that for the GC is we actually look at the same sample of gas, and then we did 20 replicate injections back to back. And then we just look at the standard deviation of that sample. And we get a relative precision depending on the concentration of gas that you put in. And at atmospheric conditions, we can expect to have 3 ppb precision for nitrous oxide, 3.6 ppm for carbon dioxide, and 20 ppb for methane. And then we can look at that as how it relates to the G2508, which will give us a measurement at different intervals. So if we just took a single measurement for the nitrous oxide, it would be the precision of that one measurement, which is the standard deviation of a small population, is around 7 ppb. And then CO2 is 500 ppb and methane is 1 ppb. So you can actually see that the GC has a stronger single point measurement than the G2508. But methane and CO2, the G2508 is significantly more precise. And then we'll see what can come of that, even though it has a smaller noise. Now we can look at the experiment that we actually take. So we used a chamber that was around 9 liters, and we closed that chamber over the soil and then let the gas recirculate through the Picarro G2508 through the external pump, which the whole system is leak tight, and we check that. And then the outlet of the pump goes directly back into the chamber, causing a mixing in the chamber. And then we also put a T on top of the chamber, and then we take a GC sample from that T with a septum on it every 10 minutes. And then we took the syringe and injected it directly into the GC so we could take out any systematic error that's involved in putting them in vials or just even storing a syringe for a longer time. And then between those 10-minute injections, while we were waiting, we put in a standard gas sample into the GC to measure, so we could track the drift of the machine and see if anything was going on or if we had unexpected drift to it. So we repeated this 3 different times. One was with a dry organic potting mix. And then the second one, which was immediately after that, we put 3 liters of water with some sodium nitrate and sucrose in it to activate some activity, since we expect the dry to be very low flux. And then we treated again with even more water and sodium nitrate and sucrose to get an even larger flux event out of this. So now we can look at what the actual data came out looking like. So these, in the orange, red, and brownish colors, are the concentration measurements measured from the G2508. And then the small blue points are the discrete GC samples. So we can actually see that the calibration for the cross-calibration measure stacks up really well with each other. And for methane, we see the error bars on the methane measurement for the GC is actually much larger than the spread on the methane for the G2508. The CO2 follows relatively the same trend, and the N2O, they're lying directly on top, but has a much smaller error bar in the single point measurements. But once you actually boil down and fit these curves, we get from a least squares fit, we get the slope, and then we also get the error. And we can see that for methane and CO2, the error is an order of magnitude, at least an order of magnitude larger or smaller for the G2508. And it actually is significantly smaller for the G2508 in the nitrogen, despite the smaller shot-to-shot noise for the GC. So what this boils down to is that we have more points to fit through, making our fit actually stronger. So what these flux actually come out like, in a low flux vent for just the first dry soil that we did, we see that we get, for the GC on the right in the blue, for nitrous oxide, the error is actually significantly larger than the determined flux rate from just fitting to that. So we'd say that there's pretty much no flux and that it's not producing any N2O. However, when we do a fit for the G2508, we can tell that there actually is a flux to a relative degree. And then the CO2, the error is tiny on it for the G2508 and falls well within the error bar of the GC. So looking at the higher flux events when we treat the garden soil, starting with the methane and nitrous oxide on the bottom, the error bar on the fitted G2508 flux is smaller and lies within the error bar of the GC determined flux. And they actually agree pretty well with just the raw number fitting together. And we can see that the flux for the N2O actually increases with our treatment, and methane is kind of doing its own thing as usual. And CO2, there's actually a slight discrepancy in the two measurements. It's about a 9% error in them, and I'm currently trying to figure out what happened there and if it was perhaps maybe my calibration was off for CO2 and the linearity. It goes out of linearity at some point, but I'm currently working on that as a new project. So as a conclusion, we've showed that both instruments show the same story of N2O, methane, and CO2 fluxes, with it ultimately boiling down to this temporal resolution that the G2508 gives us. And in addition, it gives us this great immediate feedback so we can see what's actually going on. This is, on the right is a picture of the data that we took on the first soil sample. That's why there was no determined methane flux. And we could see that the methane is kind of wandering around, not really producing at a given time or anything. And it actually, the GC agrees with the trend pretty well. But this, we determined as soon as we saw the data, we didn't even need to know that we needed to fit anything. So overall, it's just this temporal resolution that gives us great fits for the fluxes, and we know immediately what the soil is doing. So right now, I'd like to hand it over to Dr. Nick Nickerson, and he's going to talk to you about some of the research that he has done with Forerunner research and his new chambers that he created.
Okay, thanks Eric, and thanks Bill. So like Nabil and Derek said, I'm going to talk to you a bit about some soil chambers that we've been making in the lab, and those are both for the 2508 that Derek was just talking about, and the 2201, the isocarbon instrument that Nabil was talking about. So while it's still fresh in everyone's memory, I just want to say that we've been making an auto chamber for the 2508 and the 2201. So this is a typical static flux chamber. It goes up and down and measures flux at a given interval. And that can be used with the 2508. So you can measure the 5 species, CO2, methane, nitrous oxide, ammonia, and water vapor. And you can also use it with the 2201, measuring methane and CO2, and they're isotopologues. So just again, to keep with the same message that Derek had, these are some plots that of data we collected during an experimental trial. So what you're seeing here is just another potting soil, and we're doing various additions to it. So at the bottom where you see the ammonia flux spiking, what we've done there is we've added various quantities of fertilizer to the soil. And similarly, in the middle plot where you see the nitrous oxide spiking up, what we were doing there is just after the fertilizer addition, we were filling up the soil with a lot of water to try to get the nitrous oxide to go through the roof. And what we actually ended up finding was again similar to Derek's presentation, is that the CO2 because of this high temporal resolution data, we're getting very good errors on our flux rate. So for CO2, we're getting less than 0.01 micromoles per meter squared per second. For nitrous oxide, we're at 0.1 nanomoles per meter squared per second. And for ammonia, we're at about 0.01 micromoles per meter squared per second. And unfortunately, we didn't get any methane flux from this study, but I would expect it to fall well within what Derek was presenting. And the one point I wanted to make is that these chambers are fully integrated with the Picarro analyzers. So the Picarro controls all of the chamber movement. It controls, or it collects all the peripheral data, so the chamber temperature. We have soil moisture, soil temperature probes that can be plugged into the side of the chamber. And all of that data is synced directly to the Picarro hardware and directly to the Picarro data files. So that makes it, we have an easy-to-use processing software afterwards that lets you, with the click of a button, basically take all your Picarro data and all your chamber open and closed data, combine it all together, and calculate all your fluxes on the fly. So that's what you're seeing here on the right. And it has a good amount of power user features as well, so you can do custom parameters for your chamber and for your fitting functions. It also has a full Monte Carlo error analysis feature in it. And then the last point I wanted to make is that we have a multiplexer unit that's going to be ready in April of this year, and that'll allow people to do up to 12 chambers per Picarro. So now I'm just going to talk a bit about a few studies that we've done here in Nova Scotia, looking at isotopes and how they can help us understand soil flux. So I'm going to give you a brief overview, just kind of taking from what Nabil had said in the beginning. Then I'm going to look at two different studies we've done here, and that's mostly looking at separating autotrophic and heterotrophic respiration. How do we understand how plants and microbial communities are respiring in the soil? Then I'm going to talk a little bit about flux measurement with chambers and why chambers may not be the best thing to use, and then talk about the chamber that we've developed here, which we call the forced diffusion or isotopic forced diffusion chamber, which we think overcomes a lot of the biases that are present in the other chamber systems. So again, just going back to the picture Nabil had shown, isotopes provide us a really great way to trace how carbon is moving through a system. So we start with a CO2 input from the atmosphere, which goes into the autotrophic organisms. That gets fractionated by various biochemical processes as it transfers down through the leaf, down the stem, and into the root. So we get a signature that comes in and a signature that comes out that are very different. And so I'm talking about isotopic signatures here. So we get a very different rhizosphere CO2 signature. We can have very different aqueous CO2 exchange isotopic signatures. The root exudates have different isotopic signatures, as does the soil organic matter for various reasons. And so what we end up being able to do is looking based on these signatures at what's coming out of the soil from autotrophic respiration, and you can even break that down further to see what's coming from rhizosphere versus stem respiration. And then also CO2 output from heterotrophic respiration, and which again can be broken down further. So the two studies I'm going to talk about are our first one that's looking at how drought affects the CO2 output from both heterotrophs and autotrophs. And the second study I'm going to look at is looking at how we can use isotopes to understand how CO2 is respired within the soil profile. So in this first study, what we had is five sites. There were 3 in Nova Scotia and 2 in Newfoundland. And these sites a year before had been trenched, so we dug a square around a plot of soil to exclude all of the root respiration from that one plot of soil. So we were able to measure two plots, one with root respiration and one without root respiration. And then the next year after trenching, what we ended up getting was an interesting situation where we had a drought in the Nova Scotian sites, and there was no drought in the Newfoundland sites. So what you're seeing on the top here is the heterotrophic or the microbial respiration in the squares, which you can see is fairly constant during the course of the study. And so during the course of the study, the drought gets worse and worse, just so you know for later. And what you see in the triangles is the autotrophic respiration. So what's really interesting here is that you can see at the site where we had no drought, we're getting pretty close autotrophic versus heterotrophic respiration isotope signatures. But at the site where we have drought and the trees are the trees and plants are undergoing a moisture stress, what we end up getting is as the drought progresses, we end up getting a heavier and heavier isotopic signature. So that means that these plants are tending to use more 13C for their metabolic or biochemical processes. So that's interesting in several different ways. And the first is that we are able to look at heterotrophic respiration and say that it doesn't change with moisture stress. So if we're actually studying a system where we don't have this trench site, we're able to pick apart, based on the isotope signatures, what component of respiration is coming from autotrophs and what's coming from heterotrophs. But this, so we wanted to follow up on that study a little bit and see if in the lab if we could reproduce the same results. So these are some data from Claire Phillips, who was at Oregon State at the time, and she was looking at Douglas fir seedling plots. So these were experimental plots where she had a piece of PVC with either a Douglas fir planted in soil or not planted in soil. So the other treatment was just a soil column. And what she ended up finding at first was kind of interesting, and that was that the heterotrophic respiration was in fact changing with moisture stress. But what was interesting and what we actually ended up using the Picarro for was to look at her experimental setup. So she was capping these PVC tubes with a chamber, much like Derek was showing, and because she was doing that, it caused a bias in her results. So what you're seeing on the right plot here is what her bias looked like, or what her results looked like before we corrected them, based on the Picarro and the model data. And then on the left, you can see a similar trend to what we saw at the 5 field sites above, and that's that the heterotrophic respiration had no moisture content variation. So the second study I'm going to talk about is looking at how different depths of the soil can contribute differently to the total soil respiration. So you can imagine that if you have more roots at one depth, you would tend to get a more root isotopic signature than where you had more microbes, where you would tend to get more heterotrophic isotopic signature. And the way we did this was by burying tubes in the soil. So these tubes were perforated and they were covered over with a hydrophobic membrane. We attached the Picarro to one side of the tube and just let it draw air out of the tube for about 15 minutes to get a good idea of what the CO2 and the delta 13C ratios were. So what you're seeing on the top plot here is the soil concentration during that study period. So that's the CO2 concentration from 0 to 10,000 ppm. And then on the bottom plot, you're seeing the isotopic signature for the same period. And the interesting thing that came out of this study was using the traditional approach, which is to use a Keeling plot, a depth Keeling plot. What we're able to see with the Keeling plot is a little bit of temporal variation. But because the Keeling plot uses all of the points in the soil, we weren't able to resolve anything that was happening with depth. Whereas if we use the gradient approach, which is based on Fick's law, shown in the two plots on the bottom there, we were able to resolve some depth-dependent variation in the CO2 or the isotopic signature of flux. So on the left-hand side in the girdle plot, what we're seeing, the big spike that you see and then the decrease there was actually a physical effect caused by a rain event that happened about halfway through the study period. That caused the isotopic signature to change because the water was filling into the soil pores and pushing CO2 out, basically. On the right-hand plot, you're seeing the intact site. So this is what we interpret, at least, as a variation with depth due to the amount of microbial versus the amount of root respiration that's occurring. So you can see the 3 depths here are the shallowest depth is the solid line, the next depth is the dotted line, and the last depth is the or the dashed line, sorry, and then the last is the dotted line. So we're seeing actually something physical or something biological happening here, where with depth we're getting different isotopic signatures, probably because of the relative proportion of root versus microbial respiration. And then the last thing that I want to touch on really quickly from this study is that we were able to show with this data that Keeling plots aren't always linear, basically. So what we would expect from the Keeling plot is shown here in the open squares. And if your isotopic composition is not constant with depth, what you get from model results, at least, is something that looks more like the triangles on this top plot on the right. So we have a curvature in the Keeling plot which tends to bias the result quite substantially. And we were able to show that using the data from this study. So on the bottom here we have the residuals of the Keeling plot data from the Picarro. And you can see that that curvature that we're showing above in the theoretical results is showing up quite clearly as well on the experimental results. So that was interesting to validate our theoretical models. So the final thing I'm going to talk about a bit is just how chambers bias isotopic results, I guess. And what you're seeing on the left here is what happens when we put a chamber on the soil. So you can think about putting a chamber on the soil and it's starting to fill up with CO2 or whatever gas is coming into it. Eventually that CO2 is going to build up to such a level that it feeds back on the soil again. And that's what you're seeing in this plot. So you're getting a very hot, so the white and yellow colors are a lot of CO2 built up in the chamber. And then this plume below the chamber shows the CO2 from the chamber feeding back onto the soil. And what's interesting about this for isotopes is that because they the isotopes or the heavier isotopes diffuse slower than the lighter isotopes, it causes an isotopic bias in your chamber measurements. And on the right here, you're seeing a plot of that bias from experimental data. So again, what we're seeing in the black solid line here is the CO2 concentration in the chamber increasing with time. And on the bottom, what we should expect is that the delta 13C should asymptotically drop off, basically. So you see the dotted gray line there. That should be what we would expect the trajectory to be. What we actually find is that the trajectory reaches a minima and then springs back because of this differential diffusion of the isotopes. So that can cause a bias in chamber measurements of between about 0 per mil and 10 per mil. So it's pretty substantial if you're looking at natural abundance studies. And then I just want to show this again. So this is data from the Picarro showing the exact same thing. So these are 4 chamber measurements, and you can see on the bottom here the residuals from our Keeling plots, and what we're seeing is that curvature that I was showing you before. So that's going to create a bias in the delta 13C that you're measuring for respiration. So the way we've gotten around this is by using a chamber that we call a forced diffusion chamber. So this uses a diffusive membrane, which you can see here, the white membrane on the front of this chamber. And what happens is soil flux comes into the chamber and it leaves the chamber through the membrane. And because we know how fast it can get across that membrane, we're able to calculate the flux of not only bulk CO2 and other gases, but also their isotopologues. What we've done is we plumbed this directly into the Picarro analyzer using their 16-port manifold, so you can have up to 8 chambers per analyzer, and the small sample isotope module, which allows us to draw small discrete samples from the chamber for analysis. So the lab results from this were actually very, very good. What you're seeing here is a lab apparatus where we were able to instantaneously double the amount of CO2 flux coming out of the apparatus, and that causes a disequilibrium effect for the isotopes, which is what you're seeing there in the turquoise. So we were able to create an isotopic disequilibrium of about 2 per mil, and what we wanted to see is if we could track that with the ISO-FD chamber, which is what you're seeing here in the green dots or the green squares. So we were able to track that 2 per mil change very, very well, to within about 0.5 per mil error. So we're already doing substantially better than many of the other chamber systems out there. So the next part of this was we took it out to the field. We wanted to look at a real field study, so we were looking at a crop rotation where the plots either switch between wheat or a vetch, which is a nitrogen-fixing cover crop. And what we were wondering is there any isotopic difference basically between these 2 plots? So you can see here on the right we had the Picarro in the field for about a week, stuck in this tent, and it was running that whole time off of grid power. It took us about an hour to set it up, and we got no data loss during that full week, despite a few torrential rainpour events. So again, like I said, there was rain, but what was interesting, again, is that we had drought for about 30 days before, or no precipitation for 30 days before the study started. And then in about 1.5 days, we had 2 significant moisture events, which really drove the CO2 flux, which you're seeing on the top here. So the precipitation is in blue, the temperature is in red, and the CO2 flux from the vetch is in black, and the CO2 flux from the wheat is in the dotted black line. So you can see right after the first rainfall event, we had a huge increase in the CO2. And we also get a huge increase in the CO2 again after the second rainfall pulse, which we assume was basically the plants were moisture stressed at first. The first rainfall really caused them to respire a lot, but that all drained out really quickly because the soil was so dry. So the second rainfall had the same effect, basically. We were unable to observe any, so on the bottom here you have the isotopic flux, and we weren't really able to observe a huge temporal trend in that, which we were hoping. But what we were able to pick apart is that the isoflux from the wheat tends to be more isotopically deplete. So it tends to use more 12 CO2 than the flux from the vetch site. And so what we're interpreting that as right now is that because the vetch is fixing its own nitrogen and maybe it has a more nutritious soil, it's able to use heavier carbon in its metabolism without a higher cost, whereas the vetch tends to have to use lighter carbon to metabolize. So just so all of you know, most of these, except for the last study I showed, are all available in peer-reviewed publications, and those are available from our website, soilflux.com. And so now I'm going to hand it back to Nabil, who's going to be handling the question and answers part of the talk.
Thank you, Nick, for this interesting presentation. Derek as well, that was very good. So now we're going to address the questions that came through. Some of them were answering right away, and then I have compiled a list of what we have here to be able to address by Nick and Derek. Derek, I'll start with you. I have a question that came through asking, are the 5 gas species really measured simultaneously on the G2508?
So it's actually not simultaneously because we have a data rate limit. So the data rate is actually 7 seconds. So that means we'll get a new measurement every second. So that's the time resolution that you'll have with CO2, methane, water, and ammonia. And then the resolution will be 3 seconds roughly for nitrous oxide. So the real answer is, and it's not simultaneously, but it's fairly quick.
But the data will be displayed on the user interface continuously around the same time.
Correct.
Okay. The other question I have for Derek is, how often do you need to calibrate the G2508 analyzer? And most probably it's the same for the isotopic analyzer, the G2201. So, and a follow-up question for Derek is, how do you characterize the drift of the G2508?
So those two actually go hand in hand because we need to calibrate if we know that it's too drifty. So actually, we characterize the drift by using a bottle, and then we put the analyzer on the bottle so it measures it continuously for 2 days. And then we look at the peak-to-peak drift value that we get if we average for 5 minutes, so we get a better noise measurement. And it's actually it will drift for typically around 7 ppb every 48 hours, or within a 48-hour time span. So roughly, you'd want to get an idea of where you stand with standards once a day, or before you do a large-scale experiment if you need the data to be very accurate.
Okay. Nick, do you have a comment regarding calibration of the isotopic carbon analyzer during your measurements?
Yeah, so we were calibrating the analyzer every 2 hours, I think. During that field study, it's unnecessarily frequent. So we probably could have got away with about what Derek is saying is daily. We have done tests before looking at the calibration, and once again we found the same thing with the 1101. So this is the old 2201 basically, and it was about a 4-hour interval that we decided was the most accurate for. This was specifically for isotope signatures, though. The concentration is more like what Derek says is about a day.
Okay, so basically you have a lecture bottle in the field, and then you switch the valve and then be able to trickle the CO2 inside the analyzer? Is this how you did it, or?
Yeah, exactly. So we were just using a small car tire air pig, basically. So we had about 100 psi of gas with us, and it lasted us well over the week. We had about 80 psi left.
Okay. Nick, I had a question about if you can give a little bit more information about the Forerunner multiplexer, how it works, and then I have a follow-up on the ISO-FD chambers. But first, if we talk a little bit about, you elaborate a little bit about the multiplexer.
Yeah, so the Forerunner multiplexer is, so again, it's going to be ready in April of this year, and it's for up to 12 Forerunner chambers in a recirculation mode. And the multiplexer, it handles all the power supply and all the data feedback from the chambers as well. So what you get is you get all the data coming back to the Picarro through the multiplexer, as well as the gas being shuttled back and forth. And so the multiplexer is completely leak tight, and it runs off of a standard power supply, basically.
Okay. I have a question regarding the FD, the forced diffusion chamber. It says, can you tell me more about the forced diffusion chamber, how it works? And then the other question was, in that regard, is how do you maintain the soil humidity and temperature equal to the exterior of the chamber soil while it's installed on the soil, while the chamber is installed on the soil?
Okay, so it's going to be helpful to go back a few slides here, which I'll do.
Okay.
So the way the chamber actually works is soil flux comes into the bottom of the chamber through just an open bottom into the chamber cavity, and then it diffuses again out across these membranes and into the atmosphere again. And because we know how fast the CO2 can move across that membrane, and we measure the concentration of CO2 in the soil cavity here, or inside the chamber rather, we're able to calculate the flux rate of CO2, so the bulk CO2, and also its isotopologues. So there is one caveat to that, and that's that we have to, because the atmosphere is constantly changing with time, we also have to keep a reference on the atmosphere and what its isotopic composition and CO2 concentration is. So we do that through the membrane windows on opposing sides of the chamber, basically at 90 degrees. Those are just constantly in equilibrium with the atmosphere, and we're sampling those to make that correction. So in terms of making sure that the moisture and the humidity the moisture and the temperature are fine in the soil, basically the chamber is, well, based on our simulations, the chamber is small enough that the footprint of the chamber is not big enough that it stops thermal diffusion radially. So basically what we're doing is we're relying on that small footprint to allow the heat underneath the chamber, or the soil temperature under the chamber, to be the same as the soil temperature beside the chamber, basically. And the same thing applies for the moisture content. So obviously this thing, when it's left on the ground, it does create a microenvironment, and we want to move the chamber, every so often, maybe once every month or something like that. But in general, for the short term, that small footprint allows us to keep most of that microenvironmental effect out of there.
Thank you, Nick. So a quick follow-up is how often can you sample from the SSIM from the chamber into the isotopic carbon analyzer?
So for this study, we were taking samples every 15 minutes. So we would take a sample from the soil part of the chamber, and then from the atmospheric exchange part of the chamber. So each chamber measurement is about 30 minutes long, and it consists of those two measurements. So for our setup in the field, it was about two hours cycle between the 4 chambers that we had. So we would be back to the same chamber every 2 hours.
Okay. And another question is, what's the magnitude of isotopic bias in other chambers compared to the ISO-FD?
So what we've simulated in other chambers, and what some people have measured, including us, is an isotopic bias anywhere between 0 and 10 per mil, basically. And in the forced diffusion chamber, we're not able to, so in the simulations we aren't able to get any bias whatsoever in the forced diffusion chamber, and nor are we able to observe a bias in the experimental results right now, given the precision of the instruments we're using, basically. So for other chambers, it's between 0 and 10, and it depends a lot on the chamber design. And for the forced diffusion, we're sitting down around 0, basically.
All right, thank you, Nick. I have time for one more question, but I would like to let the listeners know that we will send out the recording of this webinar later on, and we'll be able to field other questions. So my email is nabil@picarro.com, nabil@picarro.com, and if they feel free to send us more questions so we can field them. The question I have here is, can the Picarro analyzers interface with other vendors' chambers? And the answer is yes, but just in the case of the Forerunner chambers, we have the software and the real-time flux measurement is seamlessly connected with the Picarro analyzer. So basically on the monitor of the Picarro analyzer, you'll see a window where it's the flux measurement coming straight from the Forerunner chambers. And you see the user interface, the Picarro analyzer user interface. In the case of other vendors, you can always interface the chambers together with the Picarro analyzer, but you won't get the seamless interface of the software the way it does with the Forerunner. At this point, I would like to thank both Derek Fleck and Nick Nickerson for the very interesting presentations that they shared with us. And I would like to thank the listeners for their attendance. And again, we will send out a recording of the webinar, and please feel free to stay in touch and send your questions or your inquiries to us, and we can field them as they come. Thank you so much.